smart contract hacking. In this video, I'm going to show you how to hack into smart contracts by applying several common exploits and how to create and test your own hacking strategies. And this is the real deal. You'll get a chance to do this yourself because I'm going to create a smart contract with a vulnerability and leave there $100 worth of Ethereum for the first person who can hack it. So make sure to watch all of the methods I'm going to teach you because you'll need them. And if you feel that I missed something in this video, you can always download the full code with all of the methods from my website. Links in the description down below. Also, this is for educational purposes only. Please do not hack other smart contracts without the owner's permission. Only hack me. So the first thing you'll need is to be able to view the code of the smart contract. While it is possible to perform attacks on smart contracts without actually seeing the code, I suggest only observing the ones for which you can actually see the code. This way we can also study the project itself and find any kind of business logic flaws which we can take advantage of. Okay, so that being said, one of the best ways to check the code of smart contracts is by going to the Ethereum Explorer and searching for the contract you want to analyze by inputting the address on the search bar. Now, the address that appears may be one of two, so either it's a wallet or it's a contract. If it is a contract, then it will have the contract tab. If the contract is verified, then it will show the source code. If not, it will only show the bytecode. I suggest that you forget about this contract and just move on to another. Now that we have access to the code, we can start to study it and check for possible attack vectors. But let's say that we did in fact find one attack vector and we would like to confirm if it is or not an exploit. And even after confirming, how would we execute the attack itself? Let's use some tools for that. So depending on your preferred language, you will have access to different tools. For example, for Python, you have Brownie, which is essentially a Web3 framework that runs on top of the web3.py. While I don't have anything against Python, we are going to use the JavaScript version, hardhat. This tool will not only allow us to interact with live contracts, but it will also enable us to download a current copy of the blockchain onto our local machines and simulate contract calls to test our attack hypothesis and confirm the exploits. This will give us more confidence when executing in a real-life scenario. So to install everything, it's really quite simple. Create a new project and open it in code. Now install hardhat by typing yarn add and let's add it on the development side, hardhat. There you go. Or install it with npm if you prefer. To initialize hardhat on your node project, simply run npx hardhat. This will pop up the hardhat configuration, so go ahead and select TypeScript. And for everything else, just press enter as we want the default configurations. And that's it. Easy, right? Now, here's a quick tutorial on how to interact with a smart contract using hardhat. What you have to know is that an interaction with a smart contract is simply calling one of its available functions. There are two types of function calls. There are reads and writes. You can check the functions that a contract has for each in the respective tags on the Ethereum Explorer. To call a readable function, you do not need any kind of authentication. In fact, you could simply call them from the Explorer. For example, in the Tether USD contract, we have a readable balance of function that returns the balance of a specific address. If we put the contract's address itself, we can obtain the balance of USDT it currently holds. To do the same thing using hardhat, go ahead and create a new script file, call it balance of, and create an asynchronous main function. So as I said, you don't necessarily need an authentication in order to call a read function. But unfortunately, I couldn't find a way to do so in hardhat, so we are going to be needing a signer. But don't worry, we're going to do this pretty easily. A signer simply consists on having a wallet's private key in order to authenticate our smart contract call. So let's create one. So create another script file and call it random wallet. And inside import ethers from hardhat and create a random wallet. Now simply log the wallet's private key and run npx hardhat run. And then the path of your script, so script random wallet. Now that we have a random private key, we can import that account by going into the hardhat.config file. To do so, create a networks property with a name of a network we want to create. Let's call it mainnet. Inside, create an accounts property And this will be an array with all of the private keys you want to use on your scripts. Because Ethereum is a decentralized network, it has multiple nodes connected to each other, sending transactions and contract information to one another. This means that if we want to get information from the blockchain, we will have to get it from a specific node. You could create your own node, but that's a topic for another time. So what we can do is go to the Chainlist website, and by clicking on the Ethereum page, we can get a list of all of the public RPC servers addresses which we can use. So go ahead and copy one and paste it on a new attribute on the mainnet called URL. Now, the only thing we are missing is the contract itself. So going back into our contract page on the Ethereum Explorer, and if you scroll down, you can see a little button here to copy the code. So go ahead and press it. And now on our project, under the contracts folder, let's create a new Solidity file and call it feathertoken.sol. So now simply paste the code you've just copied, and hardhat will compile this contract for us automatically and create our transaction calls with the proper contract function names. We just have a little problem now. So if you go back into our hardhat config file, you can see that it has a specific Solidity compiler version that does not match our current contract. Simply create an array with all of the versions you need for your contracts and you're good to go. Let's finish our balance script by first getting our accounts, create the contract from the name of the file we've just created, and create the contract object. This will receive the address on which this contract is stored and the interface of the contract and the account that is going to interact with it. Finally, we just need to call the balanceOf function of the contract with an address and log it. To run our script, type npx hardhat run and then the path for our script. And don't forget the network flag with the value mainnet, which is the name of the network we created on the config file. And as you can see, we get the same value as we did in the Explorer. Now for a writable function, for example, the approve function, we can do the same as we did with the readable one. So create a new file, call it approve allowance, and just copy and paste the code from the balances. The top 3 lines will remain the same because we are going to be interacting with the same contract. The only thing that changes is the function we are calling on the contract itself. So to make sure this function works, we can first check the allowance the contract has for our account, approve an amount of USDT for the contract to be able to spend it from us, and check the allowance again to make sure that the changes took effect. We could run the script as it is, but it is a writable call. So it will change the state of the contract, and therefore we will have to pay a certain amount of fee in order to be able to execute this. But we are professional hackers, we can do better. Instead, what we will do is fork the blockchain and test our code locally. Forking is the process of creating a new blockchain from a previous existent one. Hardhat will do this for us, and we will now have a local copy of the Ethereum blockchain on which we can test our code and, better yet, not pay any fees. So to do this, simply go to hardhat's config file and add a new network. This new network has to be called hardhat since it is the default local chain. Now, instead of having the URL and accounts, it will have the forking property, and inside the URL of the node, we will like to make the fork. We don't need to define test accounts because the hardhat network will do that for us. And now simply run your script again with npx hardhat run and simply switch the network flag from mainnet to hardhat. And as you can see, the contract had 0 allowance first, and when the approval was accepted, it now has the allowance it was defined. Bear in mind that while this is a great tool to test your strategies locally with 0 risk, in a real-world situation, you'll have to take in other considerations such as gas fees and block transaction ordering, which can make you vulnerable to front-run attacks, but I'm getting ahead of myself. And yes, you'll have to take this into account when hacking my contract. Watch until the end for more information, and the first person to hack it will get to keep the $100 worth of Ethereum that I put in there. So, on to the exploit. Okay, so the first method I'm going to teach you is not exactly a method, but rather a good practice I've already talked about. So analyzing the codes. So in here, we have this target contract, which contains all of the exploits we are going to discuss. But before trying to find any kind of exploit, let's first try to understand the contract a little bit. We can see at first that we have a few contract variables. We have an owner address and a proxy. We have a mapping from an address to an integer with the name balances, which we can assume that stores the balances of each address. we have a mapping to a mapping from addresses to an integer called allowances. I think we can safely assume that this stores how much allowance an address has of another address. And finally, a total supply integer. And all of these variables are private, so we cannot view their values. Well, actually, that's not true. You can in fact check the values of private variables, but that's a topic for another video. Next, we have a constructor that receives an owner and proxy and stores them in the contract variables. We then have a modifier called onlyOwner, which checks if the origin of the transaction came from the owner. Then we have a bunch of functions. So the first ones are the public view functions that simply return some value stored in the contract, such as owner, proxy, total supply, the balance, and the allowance of the users. Next, we have the public functions that alter the state of the contract, such as the transfer, the approve, the mint, deposit, and the withdraw. All of these functions seem to call another internal function. And then we have a change proxy function that does a delegate call to another contract, but more on that later. We then have a receive and fallback function, which, if you don't know, are responsible for executing if you try to call a function that does not exist in the contract. And finally, we have the internal functions that execute the logic of each of the public functions we've seen and alter the state of the contract. We also have a proxy contract with the same variables as our contract, but with only one function. We'll check this one later. So now that we've seen the contract's code, let's talk about the first type of exploit, function exposure. Function exposures present an opportunity to call a function that otherwise wasn't supposed to be called by the corresponding caller. This can be a public function that otherwise was supposed to be private, for example, or a function that can be called by a specific user with a specific role, but for whatever reason, the role check is not present or is incorrect. You'd be surprised by the number of contracts that unfortunately are vulnerable to this. Going into our target contract, let's check if we have any inconsistent function calls. So the view function seems fine. All of them have the view and public. The public functions also seem okay. We have a payable one for the deposit, which seems to be consistent with the contract logic. Now, here it is. For the internal functions, we can see that the approve function is public, but is this exploitable? Well, if we were to call the public function of the approve function, we could only choose a spender and the amount to spend for our account because the account to change the approval is being chosen here by the message.sender. However, if we were to call the supposed to be internal approve function, we could choose the account we want to change the approval for. So let's do that. First, create a new script and name it exploit1. Next, import ethers from hardhat and create an asynchronous function. Call it with a catch error and terminate the process if necessary. The first thing we need to do is get 3 accounts from the ethers to test. So an owner for the contract, a victim to exploit, and a hacker, which will be us. For this specific contract, we will also need a proxy contract deployed. So go ahead and deploy the proxy contract and obtain the proxy address. Then simply deploy the contract with the owner and proxy address that the constructor of the contract requires and obtain the address of the target contract. We can also log the addresses for debugging purposes. Now let's simulate that the owner gave 1 ether worth of this token to the victim by calling the mint function. We can do that by connecting the owner to the contract and calling the mint function with the victim's address and the amount of ether, which can be parsed by ethers. From here on out, we, the hackers, are going to execute the exploit. So let's first check the balance of the victim by calling the balance function of the contract with the victim's address and logging the result. If we need to check this value in a more readable manner, we can pass it through the ethers format ether function. Let's try running the code by using npx hardhat run, followed by the path of our script. Don't forget to run this on the locally forked chain by inserting the network flag with the name hardhat. And as we can see, the victim has the correct balance. Now for the exploit, let's first print the allowance we have from the victim, which should be 0 before the exploit and 1 ether after the exploit. Now call the approve function, which should be internal but it is public, with the victim's address, our address, and 1 ether of value. If we run the script again, we can see that now we have an allowance of 1 ether over the victim's balance. What we can do now is transfer 1 ether from the victim to us and check the balances of each. And there you have it. We managed to exploit the contract and steal the victim's balance by approving it on our account. The fix for this type of exploit is to do an extensive testing on all of the function calls and triple check if all of the methods have the correct permissions. So on to the next exploit, underflows and overflows. An underflow and overflow happens when a number goes beyond the minimum and maximum range respectively. It's kind of like that Simpsons sketch where Homer goes to the gas station and puts more fuel than the machine can handle, causing the value to flip back to zero when reaching the maximum. The concept here is the same, except that we have a number that can occupy 256 bits, which is a lot. So going back into our target contract, we can see in the transfer function that it updates the balances by subtracting the sender's balance and adding to the recipient's balance. But what if the sender's balance was zero? Will we get a negative number? Well, no. So, like the Homer Simpson analogy, we would go to the previous available number, which is the maximum number the slots can have. This is an underflow. Let's create a new exploit script. Like the first one, we are going to have a main function and make the owner deploy the proxy and the target contract. Let's simulate that we already have 1 ether worth of the token by having the owner mint it for us. And let's check our balance. So what will happen now if we were to transfer 1.5 tokens to the victim? Would we have minus 0.5 tokens and the victim 1.5? Well, that doesn't make much sense, right? So negative currency doesn't really exist. Would the victim have 1.0 tokens and we would have 0? Well, that makes more sense since it's the maximum balance we have. Let's print our balance and the victim's balance and check how much we would have by running the script. And as you can see, not only would we give 1.5 tokens to the victim, but we would also have almost the maximum number of tokens available, and we could do whatever we wanted with them. There are several ways to fix this issue. So one of them is to use the SafeMath library available from the OpenZeppelin group, or the easiest one, ensure that your contract is compiled with version 0.8 or higher. This is because Solidity started protecting contracts from underflow and overflow from this version on. If it were to happen, the transaction would simply be reverted without taking any effect. One of the most common exploits I still see happening in contracts are reentrancy attacks. In this type of attack, a hacker can force a contract to call back into itself before the initial call finishes executing. Depending on the contract logic, this can lead to some inconsistencies in the state of the contract, or in the worst case scenario, all of the funds being drained from the contract, as it happened in the 2016 DAO hack. In our target contract, we can see an example of this in the withdraw function. This function works in conjunction with the deposit function, and the logic is as follows. So a user calls the deposit function to send some ether to the contract in exchange for the same amount of the target token. We can see this through the message.value here, and the increment in balance with the same amount. Now the contract has X ether and the user has the same amount of tokens. If the user wishes to withdraw, they would call the respective function, and the contract would first check if the user has a positive balance, and if so, it would send the same amount of ether to the user, represented here by the message.sender call, and reset its balance to 0. It's important to note that this is technically a contract call, so much like the change proxy function, which makes a delegate call to the proxy address with the function name and values, here we are making a call to the caller of this function, passing no function name, but the value of the ether we want to send. But it is still a function call. So what if we create the contract that calls this function, and every time the target contract calls our contract, we simply repeat the process of calling the function again. This would create a loop of function calls, and the target contract would always send ether to our contract because the balance reset wouldn't be reached. And as a result, it would always meet the greater than 0 balance requirement. So to execute this, let's start by creating a new contract in the contracts folder, and let's call it exploit 3. Create the contract using the Solidity compiler version of your choice and give it 2 variables: the owner of the contract, which will be us, and the address of the target contract to exploit. The constructor simply receives the values and stores them in the corresponding contract variable. Our contract will have 5 functions. So the first one will be the deposit function, which simply calls the deposit function of the target contract with some ether coming from the caller. Next, we have the attack function that calls the withdraw function of the target. We have our own withdraw function that simply sends the amount of ether our contract has to the owner of the contract, which will be us. And the last two functions are the receive and fallback functions. If we call the withdraw function of target, we know that it will call our contract with some ether. This execution will be made in the receive function. So in order to begin the loop, inside the receive function, we simply call the withdraw function again. However, this alone will not work since the target will eventually run out of ether, and when we try to withdraw again, the transaction will revert. So to ensure that we exit the loop at the right time, we simply recall the withdraw function if the target contract has at least some amount of ether. If not, then we do nothing and just finish the transaction. So let's test this by creating another script with the same initial values as the previous ones. And now let's simulate the contract owner sending a significant amount of ether to the target contract. This way we have an incentive to hack it. Log our Ethereum balance and the target's Ethereum balance to ensure everything checks out, and then run the script. Okay, so everything seems okay. Now for the exploit, we first need to deploy our attack contract by passing our account and the target address and obtain the address. Deposit some ether so we have at least some balance to meet the withdrawal requirement, and then simply execute the attack. If we log the Ethereum balance of our contract and run the script, we can see that the attack worked and we have the ether that was on our target contract. Now we simply need to withdraw the ether from our contract to our wallet and log the values just to check if everything is correct. After one final run on our script, we can see that the target's balance is 0 and all of the ether went into our hacker's account. To fix this, we have two options. We can use a lock mechanism, which is basically a modifier that checks if a function is already executing, and if it is, it does not allow anything else to execute. Or in this case, we can simply reset the account balance before calling the sender. This way, if it tries to call again, it will fail the requirement since it will have a balance of 0. This next exploit is not much of a technical one, but more of a social one. It can be applied to almost every contract that has some kind of check to the origin of the transaction. Looking at the example of our target contract, we can see that we have a modifier called onlyOwner that checks if the origin of the transaction comes from the owner. If so, then the rest is executed, otherwise the transaction is reverted. The only function we see using this check is the mint function, which means that only the owner can mint new tokens to a new account. Nobody else can. If we try to call this function directly, it will fail for sure because the origin came from us and not the owner. This is almost the same as the message.sender variable, but with a huge difference that makes it possible to exploit this. Let's take into account our previous exploit. If we, the hacker, were to call the withdraw function, then the message.sender value would be our wallet address. But we didn't call it with our account. Remember, we call it with our exploit contract. And our account simply called the function from that exploit contract. So in this case, the message.sender value would be our exploit contract's address and not our account address. That's where the transaction origin is different. If we take that into account here, then the value would always be the address of our account because that's the original caller. Even if it passes through several other contracts or functions, we were the original caller, so the value would always be our address. So how can we exploit this? Well, let's first create another contract and pass in the owner, which will be us, the target address of the contract to exploit, and the amount of tokens to mint. This contract will only have one function with an enticing name like get free money or something like that. And it will simply call the mint function of the target contract with our address, which will mint tokens to us with the amount we previously defined. And that's it. Well, not quite. The only thing missing is the more complicated part, which is convincing the contract owner to actually call our function. Let's create a script to test this. Deploy our contract with our address, the target contract's address, and the value of tokens we want to mint. Log the balance of our account before and after the exploit just to check if everything went well. Now let's simulate that the owner did in fact call our function. Run the script, and as you can see, we managed to mint new tokens into our account with the help of the owner without them even realizing it. So what happened? Well, because we managed to make the owner call our contract, and our contract calls the mint function of the target, then the transaction origin will be from the owner of the contract and it will pass the requirements. The tricky part here is convincing the owner to actually call our contract. To fix this, simply change from transaction origin to the message sender and please only use origin of the transaction if you know what you're doing. This last exploit can be a little bit tricky to understand and even trickier to find it and test it, but it is a good one. If left unprotected, it can lead to serious malfunctions in the contract state, making it vulnerable to the withdrawal of the funds, or in the worst case, making the contract obsolete. The exploit is called storage collision. So, to check if the contract is vulnerable to a storage collision, we simply need to verify if it has a delegate call, such as the one present on the change proxy function of our target contract. The main difference between a regular call and a delegate call is the context. So, if we were to make a regular call, the message.sender on the called contract would be this contract, and any changes made would be on the other contract's state. A delegate call is more like borrowing a function but applying it in this contract. This means that whatever changes that the other contract will make will be in the state of this contract and not the other. In this example, we will make a delegate call on the proxy contract using a new address. If we check the change proxy function of the proxy contract, we can see that it only changes the proxy state with the new address. However, because this is a delegate call, the value will not be changed on the proxy contract, but rather on our target contract. Let's examine this in more detail by creating another script. Log the address of the proxy contract and the proxy variable inside the target contract. Then simply run the script. We can see that they have the same value, which is expected. Now, call the change proxy address from our target contract with a new random address, such as the victim's address, for example. Remember that the target contract will make a delegate call to the proxy, changing the proxy address stored in the contract. However, because it is a delegate call and not a regular call, it will change the state of the target contract and not of the proxy. So log the values again, and we can see that the proxy address in the target contract has indeed changed to the victim's address. So now you must be thinking, why would anyone do something like this? Well, a good use case for this kind of delegation is the ability to change future contracts. Because smart contracts are immutable, we can use the delegate function to execute some kind of implementation of another smart contract. In the future, if we need to update the logic, we can simply create a new contract, deploy it, and change the proxy address to that newly created contract. This is one of the ways to update contracts. So, how can we exploit this? Let's take another look at our proxy target contract. We know that it simply changes the proxy state variable, but what does this really mean? Let's forget about all of these variables for a second and focus on the owner and the proxy. Where are these two variables stored? Well, like most programs, variables will be stored either in the memory or the disk of the machine. This can be represented by something like arrays, and the way Solidity does this is by placing the variables in the memory position from the top to the bottom. So in this case, the owner will be stored in position 0 and the proxy would be stored in position 1. When we say we want to update the proxy, we are basically saying that we want to update the value stored in position 1. So let's try something interesting. Let's create another contract and do the same as the proxy contract. Only this time we will switch the owner with the proxy. Do you see where I'm going with this? Now deploy our exploit contract, get the address, and change the address of the proxy on the target to our exploit contract. Log the values and run the script. We can see that we changed the proxy address to point to our contract. So nothing unexpected here. Now, the target contract will call our exploit contract when executing the change proxy method. Only now we know that our exploit contract has the values switched. Let's log the address of the owner, the hacker, and the target contract's owner. Now, let's execute the change proxy again, but this time let's pass our address. Log the values again and run the script. As we can see, we managed to change the owner of the contract to the hacker's address, giving them full control of our target contract. All of this happened because we switched the variable positions. This caused a storage collision where changing the proxy would also change the same position where the owner was saved in the target contract. To avoid this, when updating proxy contracts, the developer has to ensure that the contract variables remain in the same positions as the caller contract. So now I have a challenge for you. I want you to use the skills you've learned in this video to hack my smart contract. The first person to do this will get to keep the $100 worth of Ethereum that I put in there. I will leave the contracts and the code link down in the description below, so good luck. And if you don't win, that's fine. I'll probably do more of these challenges in the future, so stay alert. Now there is a lot more to smart contract hacking. I just scratched the surface here, but I wanted to get you started. It can be an overwhelming world, but also quite fun. You can even become a white hat hacker and win substantial rewards from smart contract audits. I hope this helped you with the basics, and again, don't go around hacking smart contracts without the owner's permission. If you don't have explicit permission from the owner, it is illegal. Hack your smart contracts, hack my smart contracts, I'm giving you permission to do so. Anyways guys, that's about it. I hope you guys liked it, and if so, please hit like and subscribe, and good luck with the hacking challenge. I'll post the solution once the smart contract is hacked. Until the next one, cheers!